me when we are live.
Done. Ready.
Okay, good evening everyone and welcome to the lecture series of Navrachna University School of Environmental Design and Architecture. Today we have a very special guest, Professor Dr. Ganapathy Mahalingam. And I'm using the word very special because he is very special for three reasons. One is that we have an institutional tie-up with his university in the United States, that's North Dakota State University. And we have had these wonderful opportunities in the past few months where we have been interacting on things that we are doing together, and we have been working out on things that we will be doing together. Professor Ganpati is also advisor of our newly set up Heritage Research Center. Uh, and the second reason why we are saying that we have a very special guest is because Professor Ganpati is a school friend of our provost, Professor Nilay Yajnik. And for that very reason, we thought rather than me introducing Professor Ganapati, it would be wonderful if I can invite the school buddies, if I can invite Professor Nilay Yajnik to introduce his friend to all of us, and then invite Professor Ganpati to give the lecture.
Thank you.
Yeah.
Thank you, Professor Pratyush. Thank you so much. And yes, Professor Ganapati and I go back 50 years. You know, we were school kids and not even teenagers since we knew each other. And, you know, I'm so grateful and so thankful that Gana, what we call Gana, I mean, whom we call Gana, is actually today with us in our midst today. Professor Ganapathy Mahalingam is a brilliant and an interdisciplinary person. You know, he's one of those rare people who has interests in areas ranging from architecture to computer science to design to mathematics to Indian philosophy to Indian classical music to Western classical music, and of course pop and Western music. So a very, very multidisciplinary person with a lot of in-depth understanding of these kind of areas. So, and that fits in brilliantly with our core philosophy of our university, which is also being interdisciplinary. And we want our students to be able to think along such lines as well. And Professor Ganapathy was actually instrumental in getting this collaboration between Navrachna University and the North Dakota State University School of Architecture and Landscape Architecture. So he reached out to me and the discussions were going on for several months. And we, of course, were very happy to tie up with him and his university. And things have already started moving. And as Professor Pratyush mentioned, the first, you know, we had guest lectures on both sides where our faculty were also invited there. We had their speakers also coming here. Professor Pratyush was on the jury of one of the awards of the School of Architecture of North Dakota State University. And Professor Ganapathy is on our, not only on the board of our collaboration, but also on the board of the Center for Heritage, Heritage Research, which is a very new center and something, again, very close to Professor Ganapathy's heart. So I'm so grateful today, and he's going to talk to us about a very interesting area, which is actually, if you know, his PhD in the field of architecture from the University of Florida is all about the computing and design of various curvatures that you see in auditorium. So it's a very interesting kind piece of work that Professor Ganapathy has been involved in. He was also the chair of the department of his School of Architecture department. So a very wide and multifaceted personality. And like all of you, I too am so keen on listening to Professor Ganapathy's talk today. And welcome, my dear friend,
Thank
Ganapati.
you. Thank you very much.
Thank you.
Thank you, Provost Nilay Ajnik and Dean Pratyush Shankar for that kind introduction. It's a pleasure to be here with you and present this lecture to your students and faculty and the larger community that you serve. It's like coming back home and giving back to a community that was part of my early life. So it's a very important thing that I do when I come back and talk to all of you and present my work. Thank you again for that kind introduction. It's a pleasure and a privilege to make this presentation to you. So with that, could I get started?
Sure.
Okay. Is the screen visible?
Yes, sir.
Yes, it is.
Okay, good. What I thought I would talk about today is something that's very close to my heart, and it's been a passion of mine for a long time, which is to think about the computability of design and what it means to compute designs. I've been thinking about this for a long time. This path started for me when I was in graduate school and has been with me on my journeys since then until the present time. So I want to begin by giving you a short background of where I came from and what this path has been like, and then get into the main presentation. I was born in 1961 and raised in Chennai, India. So, like I said, it's like coming home to me, making this presentation. I was privileged to attend Don Bosco Matriculation School in Egmore, Chennai, that Provost Yajnik mentioned. It's one of the premier schools in the country. After that, I studied architecture at the School of Architecture and Planning in Chennai, which was then affiliated with the University of Madras, and received a 5-year professional Bachelor of Architecture degree. After that, after finishing my internship, I came to the United States to pursue a master's degree at Iowa State University in Ames, Iowa. And in a year, I earned my post-professional master's degree. And after I finished my degree, I had the opportunity to teach in the College of Design at Iowa State University for a year. And then I returned to India and engaged in architectural practice for a couple of years. And then I left again for the United States to work on a PhD in architecture at the University of Florida, which I wrapped up in 93, and the degree was awarded in 1995. I joined the faculty at North Dakota State University in 1993, and I've been there since, from an assistant professor to an associate professor to now being a full professor. I also served as an administrator at North Dakota State University, both as an architecture program director and as the interim chair of the Department of Architecture and Landscape Architecture. So that's my journey, and I've been working in the field of computer-aided design and architecture since 1985. And there are a lot of things to remember and put forth in connection with this journey. Like in the Indian tradition, you always pay obeisance to your teachers and your mentors first. So these are my mentors. When I arrived in Ames, Iowa, at Iowa State University for my graduate education, I met Professor Rabindra Mukherjee, who was then the interim dean of the College of Design. And naturally, I invited him to be the chair of my graduate supervisory committee. And he was my first mentor. He's also a founding member of the Association for Computer-Aided Design and Architecture, Acadia as it's known. So he introduced me to Acadia in those early years. And little did the two of us realize that one day I would become the president of Acadia. It must have been a gratifying thing for Professor Mukherjee that I went on that path and achieved that distinction. So he's the one who started me on the path of investigating and thinking about computer-aided design in architecture. And those were the early days, 1985, PC had just come out, the IBM PC, AutoCAD had just come out, and computer-aided design in architecture was in its infancy. So after that pioneering work at Iowa State University, I went back to India and practiced for a couple of years after teaching at Iowa State University for a year. And I found that the technology had not caught up in India. So I started thinking about coming back to the United States to do a PhD. And I got that opportunity at the University of Florida. And when I landed there, I met two of my other mentors. Professor John F. Alexander was a professor in urban and regional planning and electrical engineer by training and a PhD holder in environmental engineering. He introduced me to Smalltalk, the programming language, and object-oriented computing. And he's the one who pushed me to graduate from being a user of these tools to a creator of these tools. The other mentor is Professor Gary Seaboyne. He introduced me to architectural acoustics and everything about auditorium design. And I just took these two mentors and their guidance and created what would become my doctoral dissertation. So a lot of these things that happen in the evolution of computer-aided design and architecture, they have a history, they have connections, they have paths that you follow, and you don't arrive at a point without having a journey. And it's important that we recognize all our journeys and we point out how everything came to be what it is. Now here's the question that's central to my presentation. Why do we need to think about the computability of design? Why do we need to think about that? In the last half century or so, in my lifetime, computer technology has evolved so much that many of the design tasks and activities are now performed using computation in computer-based systems. The analysis of design problems, the synthesis of design solutions, the prediction and evaluation of design performance. No, you cannot think of doing any of these things without using a computer-based system or computational processes or software and hardware and peripherals. Now it's been extended into the realm of actually fabricating and constructing our designs. So we have robotics and we have all kinds of machines that shape materials and convert them into assemblies. And so fabrication and construction is also being driven by computer-based systems and computational processes. So the question becomes critical because we need to know this transformation that's happening and what it's doing to the activity of design. If design has become computable, what does that mean for the quality of design and what we create as design artifacts? So this is the right time to think about it. We have half a century under our belt, lots of developments in the field of computer graphics, and we can see that in the movies that are made now with visual effects, all based on computation. A lot of advances. What does the computability of design mean for design, both now and into the future? One of the common misconceptions is that computation is numerical calculation. Even though a lot of numerical calculations like the arithmetic operations, addition, subtraction, multiplication, and division are performed on computers, numerical calculation is not computation. Computation is something else. And what is it? Computation, to define it in the abstract, is a process that changes input states into output states using logical operations. Quite simply, it is just that, changing an input state into an output state using logical operations. This is the most abstract definition of computation. Now, these input and output states can be represented as a binary pair of presence and absence, what we use the numbers 1 and 0 to represent. So the binary pair of presence and absence, represented by 1 and 0, are your input and output states. So all you're doing in computation, you're changing ones and zeros into ones and zeros. And can this abstract process drive something as subjective, as artistic, and as personal as design? Logical operations in computation are performed using logic gates that map an input state to an output state. A logic gate can be an ideal device or a physical device that's implemented in hardware using vacuum tubes, transistors, capacitors, resistors, all kinds of electronic devices. So these logic gates, if you just give you a sense of how many of these are there, a microprocessor in a computer has over 100 million logic gates. So what are these logic gates? This is a truth table of logical operations with two input states, P and Q, and an output state. On the top row, you have all the logical operations. You have the two inputs, P and Q, and we have T for truth and F for false. And T can be considered 1 and F can be considered 0. And then you have a mapping. If P is T and Q is T, that is P and Q are 1, for the NOR logical operation, the output is F, which is 0. So using this truth table, you can construct logic gates. And in fact, some of these logic gates are universal logic gates, like the NOR gate and the NAND gate and the NOR gate. Those are logic gates which you can use to construct all the other logic gates. This kind of truth table was made popular by the philosopher Ludwig Wittgenstein in his book Tractatus Logico-Philosophicus. But this is the core of computation. You have the inputs on the left and the outputs on the right. And all computation does is maps the inputs to the outputs. Now, how does this become powerful? You have these logical operations, and then how does it become powerful in design? And the answer is with the development of computer graphics since the mid-1960s or early 70s, if you want to use Ivan Sutherland's Sketchpad as the beginning point, the representation of three-dimensional forms in computer graphics enable the application of these logical operations to those three-dimensional forms. And that's where I think computer-aided design began, when you could apply these logical operations to three-dimensional forms. The three-dimensional forms were represented through boundary representation, which is a three-dimensional volume bounded by surfaces. This is still being used in NURBS modeling, or constructive solid geometry, where you built up a three-dimensional form using primitive elements of platonic solids like cones, cylinders, spheres, and tori. So with the representation of three-dimensional form in computer graphics, it became possible to apply these logical operations to the forms. And you can see this in the familiar Boolean operations we use to manipulate forms in CAD systems. The first example on the left is union. The second example in the middle is difference. And the third example on the right is intersection. So counterintuitively, the union of Boolean operation is based on the logical operation OR, and the intersection operation, Boolean operation, is based on the logical operation AND. So there are different ways in which these logical operators and logical operations map onto the manipulation of form and the creation of complex forms in design. And so we have a path that goes from logical operations to Boolean operations that manipulate the forms that we use in design. So why is computation powerful? It's because when we represent input states and output states, we can represent them using light, sound, touch, just to name a few states, and you can represent them on the computer, and then you can manipulate them using these logical operations. Pixels on your screen, they're just little points of light, or sound that you hear from your computer speakers, or haptic surfaces that you can touch, like the touch screen of your smartphone. All of these things are computational representations using hardware, where the input state and the output state are represented as light, sound, or touch. Once you have these computer-based systems of representation, you can represent lines, shapes, colors, textures, three-dimensional forms, sounds, text, and so on. So the power of this representation enables various human tasks. You can do shopping, you can do banking, you can do so many things through computational processes. The question of the day is design one of these tasks? So what is design? Design is a process of defining things that do not exist yet, and then predicting their performance if they were to be created in the future. This is a simple, compact definition. You don't have it existing yet, but yet you want to define it and you want to predict the performance of the design if you were to create it. So the definition of a design is in the form of representations, and we have sets of conventions for each type of representation. So we create representations of designs as if they could be built and would be built in the future. So lines, shapes, colors, textures are all used to represent a design. Words, both written and spoken, are also used to represent a design. So we have these representations that define the design, what is to be built, what doesn't exist yet, for what we need to predict the performance, and what we wish to create. So we create these representations. So if all these representations can be created on a computer-based system using computational processes, so on the face of it, looks like all the activities of design in creating design representation can be performed through computable processes. So the computability of design should be moot, right? We should think, well, all these processes like creating representations are now computable and can be performed on computer-based systems. So design must be computable. So the computability of design is not a huge debate. But then there's another layer. Okay, what guides the creation of these design representation? The design thinking that guides the creation of these representation. Now, is that computable? Now that becomes a very good question. So does that design thinking occur independent of the process of creating design representations? Or is it an activity that's performed through the design representations where the representations are models or instruments? It's a very important question. So if you ask, is design thinking computable, it becomes a much more profound and complicated question. So let us look at design thinking. What does that involve? So if you ask that question, we come to the two components of designs, materials and space, solid and void. When we design, we define the forms of materials and we define the spatial arrangement of materials, and thereby we define spaces. We specify how these materials are shaped and how that unfolds in time. And then once we have the spatial arrangement of our materials, we want to show how it is to be experienced and how it performs in a time and in a context. So quite simply, we define materials, we define space, we define materials and arrange them in space so that they define space. Seems like conceptually very simple things that we are doing. So you ask the question, can we create these forms of materials and these forms of spatial enclosures through computation? The answer in the development of computational technologies has been a resounding yes. We do this by creating building topologies. A topology is dimensionless. It is just a connection of vertices, edges, and faces. We can parameterize these topologies by adding dimensions to the edges and by manipulating the spatial location of the vertices. So when we define the forms of materials and we define the forms of spatial enclosures, we're basically defining their topologies. Now, how can we use this to develop something interesting? So this is what I did in my doctoral research. I built a topological model of a proscenium-type auditorium, and it was a complex topology with variant parts like the balcony that could be added in the topology. So I created this topological model of the auditorium. And then the vertices, edges, and faces of this topology, I calculated using performance criteria. So the topology itself was dimensionless, but the dimensions and the locations of the vertices and the dimensions of the edges could be calculated from performance criteria. So they became parameterized. And this is what I came up with for my doctoral dissertation, an auditorium design system where you have the spatial enclosure of the auditorium as your output. And then you have all these different parameters that you see at the bottom on the right-hand side with the slider settings, where you can set the seating capacity, the area per seat, the sound loss level, time delays, seat widths, depth for visual clarity, and some acoustical parameters like reverberation time and treble ratio. And you could generate this topology, this form of the spatial enclosure. So this was a design system, and I'll tell you why I called it that. Before we go into that, I'll show you this in action. This was created using the small talk programming language in the visual works software development environment. So I'm going to play this. You can watch it change in real time as the parameters are changed. So as the parameters, the blue sliders are changed to different values, the design of the auditorium changes to reflect the changing performance criteria. Some of them are viewing parameters, some of them are other parameters, acoustic, programmatic, functional parameters. So as you change the parameters, the form, the essential aspect of the design, the form of the spatial enclosure keeps changing to reflect the changing parameters. And if there are performance criteria, it reflects the performance of the design in the sense that the design that is resulting will produce that particular performance criterion. And it's a fully functioning piece of software that is now available commercially. And this was my work in making design computable through my doctoral dissertation. And this prototype was first completed in 1991, and the coding completed in 93. And I finished my defense in 94, and it was presented at a conference in 1997 and published in a journal in 1996. These years are important because the World Wide Web came into existence in 1991. So this was at the same time when the World Wide Web and the internet were being launched. In 1991, I had a working prototype of this system. So this is way ahead of all the things that you see in parametric design now. So why is this a design system? Why do I call this a design system, and how has it made design computable? One of the core processes in designing is the creation of spatial information from non-spatial information. If you looked at all those parameters, a lot of them were non-spatial, they were numerical. And I had to convert that non-spatial numerical information into some kind of spatial form, the form of the spatial enclosure. And so whenever you convert non-spatial information into spatial information, you can be said to be designing. So when you convert non-spatial information to spatial information in the context of design, you can be said to be designing. So a system that converts non-spatial information to spatial information can be a design system. So the auditorium design system creates the form of the spatial enclosure of the auditorium and dimensions it according to the performance criteria. And it does this through an algorithmic process. The whole system is defined through algorithmic processes implemented in the Smalltalk programming language in the VisualWorks software development environment. The complete system is run through computer software code and a set of algorithms written in a programming language. So the whole thing is being computed. The whole design of the spatial enclosure is being computed every time you run the software and you set all the various parameters. So I can safely claim that this is a design system and say it's creating spatial information from non-spatial information. But then you can say, granted, the algorithmic process is creating the spatial enclosure or the graphics for the spatial enclosure, but at some point in the programming of the software, you had to connect the vertices and connect the edges in the software code. So you were in fact specifying the form, the topology. So to take this kind of system another level higher, you need to develop generative processes that can construct these topologies rather than have them specified as a type, like the proscenium auditorium type. So you need to be able to generate topologies and parameterize them through computation. And then you have a system that is designing like a human being. So there is still another level to go, even though the system does something very impressive. There's another level to go before these computational systems start to design like human beings, where they start to construct topologies, parameterize them, and then you have a system that is designing in the full. So how was this possible? This was possible because of a concept called virtual computers. I use this concept rather than use object-oriented computing because this is more profound as a concept. So what is a virtual computer? You have a physical computer. Now, if you have a programming construct, which is a computational object, and you can map that programming construct onto the physical computer, then it is a virtual computer. It's a virtual computer that's been mapped onto the physical computer. And you can map millions of such virtual computers onto a single physical computer, and millions more if you have a network of computers. So this representation of computational objects as virtual computers made the programming and the realization of the auditorium design system possible. It projects a new kind of design methodology through computation, where you have all these different computational objects or virtual computers that represent the spatial enclosure objects, the grid object, and the ordering system object. And all these computational objects or virtual computers start interacting with each other, much like the Internet of Things that has emerged right now. They start interacting with each other through this computation and communication, which are essentially possible in a language like Smalltalk, programming language like Smalltalk. And this is very interesting because each one of those spatial enclosures could be a spatial enclosure for an auditorium, a restaurant next to the auditorium, and some other structure, and then a grid object and an ordering system object. And then they could all start communicating like computers on a network, like an internet, and they can generate a design solution. And some such technologies are already emerging for collaborative processes to create designs. What's interesting about this diagram is this diagram was created in, I think, 1993. And we're talking about Internet of Things only in the last few years, even though that technology has been in incubation for some time. So eventually, when you represent all architectural objects or design objects as virtual computers, then the design process becomes communicating computers and computation. I want to digress a little bit here and talk about three works in philosophy and how they have a tangential but profound relationship to computation. Being and Nothingness by Jean-Paul Sartre. It reflects the binary pair presence and absence, 1 and 0. Either or by Soren Kierkegaard, reflecting the transformation of input states to output states and choosing how an input state becomes an output state, either or. And The Eternal Becoming by Andre Bergson, which talks about the constant transformation from presence to absence in creativity. So these are three philosophical works, but they seem to embody computational concepts at its core. So you have being and nothingness, one and zero, either or, choice between input and output states, and the eternal becoming, the constant transformation in computation from presence to absence. So in design, in conclusion, if we will into presence, that we say, this is the form that the material shall take, this is the form that the space shall take. And if we will that into existence with lines, shapes, colors, textures, and we will them into presence and we will them into absence, and we do this through logical operations, and we constantly transform what is present and what is absent, what should exist or what should not exist. The philosophical core of what we do when we design is computation in the highest and most abstract sense. So if we will things into presence, if we will things into absence, and we transform them through logical operations, and we constantly transform that which exists into that which does not exist, or that which does not exist into that which exists, you're really performing computation in its highest and most abstract sense. And in a real sense, in the design context of architecture, interior design, urban design, and planning, you can perform all the activities that you perform during a design process with these high-level abstract operations. So in the end, if you ask, is design computable? My response would be, isn't it already a form of computation in its most abstract and highest sense? So thank you for your patience and listening to me. I would like to entertain some questions. Before I do, let me put some references on the screen. That is my doctoral dissertation there. It's available on the web. And then there's a website link to the software company that I've founded that sells the auditorium design system.
Thank you. Thank you, Professor Mahalingam, for this wonderful lecture. And also it's an extremely in-depth conceptual presentation that you have made today. So thanks a lot for this quite an amazing insight that you are giving to us. And I'm sure my colleagues here will have some interesting questions. And but I had one, and I thought maybe I'll take the liberty to ask you this question, because I'm kind of thinking aloud here, because when somebody says that design anyways has always been computable, right? And that's the central premise of what you're presenting here. What is the kind of counter arguments that you have met with? Because one whole kind of school of thought would say that the question of subjectivity of design, or the questions of meanings that cannot be captured through numbers or through kind of parameters. And I'm
Yeah,
referring here to meanings that are more social meanings or cultural meanings or symbolic aspects of the design. Is that computable?
yeah, that's a very good question, and it's often brought up in the context of discussions of computability of design. When you get into the realm of meaning, one must understand that the creation of forms of material and the spatial arrangement of materials into spatial configurations can be done in complete silence. So the creation of a material form, like shaping a brick or arranging a brick into a wall can be done in complete silence. So I have with me that philosophical viewpoint where this computable dimension is in the realm of architecture being created in silence. You create the forms of the material in silence. You arrange the materials in space in silence. And meaning is applied. It's something that you bring to the material or you bring to the spatial arrangement of the materials. So that can be applied equally to the forms and spatial arrangements that you're creating through computable processes, because the meaning and the symbolism is an applied process. So if you can create a complete building in complete silence and have it still work as a building, and that's why I admire architects like Louis Kahn and Tadao Ando. They don't talk much about, Kahn did talk about order in his designs, but a lot of these architects, they just wanted you to go and experience the silence and the light. And at that level, whether you compute the form or you shape it with your hands, if you're doing it in silence, then it becomes a viable proposition. So you can apply all the meaning and symbolism you want to a computer-generated form as you can to a form that you hand rendered or you drew with your hand. So it's an interesting question how people tackle that. They somehow dismiss the computer-generated form as incapable of harboring meaning, which is not fair, I think.
Thank you for that, Professor. Are there more questions? I'm sure in the faculty group. Shantanu?
Yes,
Professor Malingam, can I request you to stop sharing the screen?
Okay, I'll do that.
That is, your whole you'll be seen completely on the screen.
Okay.
Thank you.
yes, Professor Ganapati. What I wanted to understand is currently there's a huge trend on parametric architecture,
Yes,
which they use a lot of computing for.
yes.
Would this be defined as the father of that?
I will leave that to the historians of the development of computer-aided design and architecture. The first prototype was created in 1991, and 92 it was refined and presented at the ACSA Technology Conference in San Diego. 93, I had to wrap it up for submitting my dissertation. 94, I defended my PhD. So by 95, a fully robust prototype was ready. So you can put that in its historical context and see when the discussions of parametric design started in the field of computer-aided design in architecture, and where this fits in that continuum of research and development. I'll leave that to the historians. I don't have any specific claims to what it is or its significance. So.
Right. No, I mean, it was a very interesting presentation. The way you took students through this, I mean, they actually went through the steps, and instead of looking at it as just science fiction, they know they can get to it.
Yes.
So good inspiration for them. Thank you.
Thank you.
Yeah, that's it from me.
Thank you, Shantanu. Professor Nilay, you have something?
Yeah. See, these days, there's a lot of thoughts and a lot of hype actually about design thinking. And design thinking is something which is applicable and is now being considered even in areas which are totally unrelated, seemingly, to design and architecture, like business or like marketing or like product or customer interactions. Um, but one of the key things in design thinking is being able to understand that it is not what we want or what our company wants, but what the customer wants. And this is possible through observation. A lot of observation has to actually happen. So people actually go to a certain place where the problem is, defining the problem, and go there, watch how people buy. Let's say if it's a customer situation, watch how people buy or how they shop maybe, or so on. So those aspects, how would you be able to put that in the computability of design, or would it not be possible? Or would it be possible to combine both the computability as well as the software aspects?
Uh, in the development of my system, the auditorium design system, all that comes in through the performance criteria. The performance criteria are derived from things that you point out: observation, mathematical modeling, statistical modeling, empirical evidence, experience of prior architectural acousticians. So all those performance criteria that you saw being set in the auditorium design system, those numbers come from somewhere. They come from observations of architectural acousticians. They come from scientific studies. They come from mathematical models. They come from statistical analysis. So they come from the types of activities that you are describing. So if you have a performance-based design system that is generating the design solutions based on performance criteria, you're bringing all those aspects into the computable process through the performance criteria that you're using to parameterize your design solution.
Mm-hmm. Okay.
So that's how they come in. They come in through, it looks like numbers, but they're all based on, each one of those numbers has like 4 or 5 references in my reference list in my dissertation.
Mm-hmm.
So,
okay.
yeah.
And another question, because your talk brought back a lot of memories of the 80s, and especially when you spoke about small talk and the languages of that era, whether it's Pascal or, and not only that, but even many of the CAD/CAM solutions that were coming out in that time, in that era, like SDRC or ArcInfo, and of course AutoCAD, which you mentioned. In all these, I remember there were the solutions or options were available in the library, in the form of a library within the software. So the what the actual designer and the engineer had to do was just plug and fix in a way, with a little bit of tweaking here and there. So would the computer, is it necessary, for somebody who's, let's say, using ArcInfo or AutoCAD to understand the how these libraries were made through various computational techniques?
Yes, when it began, you're referring to possibly the use of blocks in AutoCAD.
Yeah.
When this technology started, it was a static representation. You would have the representation of a chair and a table in plan, and you would take that block and you would put it in your plan or place it in your plan, and that was it. You could use that chair over and over again, or that table over and over again, and make it a part of your plan, and you use that in a static way. The technology has evolved, and I think my dissertation was part of the transformation as these blocks became parametric objects that then you could set their performance criteria and then plug it into your design. If you looked at my software in action, at the end, it was exporting that spatial enclosure as a DXF file that is read by many CAD programs. So a designer could set all these performance criteria, generate the spatial enclosure, and then export the DXF and then just plug it into whatever building they're designing. So if they're designing a complex with multiple auditoriums, they could design all the different auditoriums using my system, export it as a DXF, and then plug it into their design project. So in a sense, that the reuse of these objects, parametric objects now, has become kind of a aid in the development of complex projects. You don't design everything yourself. You can get input through these parametric components, and you can plug and play with all these components and derive your own specific context-bound design solution. And that becomes, so you start incorporating, it moves towards collaborative design. So all the know-how and the expertise are embodied in these parametric objects. You don't need to know how a particular acoustical parameter transforms the space, even though it's wise to understand and know how it does. But you could use the parametric object by setting the performance criteria and then getting an approximate design solution. I would say my system generates what are called candidate solutions. It's not the solution. It's a candidate solution based on all the performance criteria that you set. So yeah, this has been an evolution. When I started with AutoCAD in '85, I was using blocks. So in a way, that has always been at the back of my mind in my evolution further down the path. So.
Okay, thank you.
Thank you. Thank you, Professor. If there are no more questions, then we can, I think, conclude the session. It's getting late. So, Professor Mahalingam, this was really wonderful, and I was actually discussing with my colleague while you were giving the lecture that it would be wonderful to have you work with our students, along with your students, and to really take this work forward in the context of our country. It could be social housing, or it could be any other topic that are very relevant to India. And it would be wonderful to actually invite you to do a studio or do a workshop. But we would be very much interested if we can work a whole studio structure. Have even professors like Professor Shantanu, who are themselves very much interested in building science and technology interface. And I think something can definitely be worked out.
Yes, interestingly, this semester I'm offering a studio to the graduate students in architecture where they're creating software products for the design professions in developing economies. Many of them are developing products for India. Some products are like creating a climate-based design visor based on the Mahoney tables. Another software is to connect NGOs in India with people with disabilities or communities with disabilities. Another project is connecting young architects in India to clients. Another project, it just is to use augmented reality to help construction workers who are illiterate to understand how to build things. So number of projects. I'll be glad to share the work of my students with your students and faculty once they're at a stage where they can present their products, prototypes, and ideas, which should be later this semester. So if you're inclined, we could arrange a session where our students share their work with your students and faculty. This is something we did on our own this time. We would love to have the studio offered again with cohorts from India and other places.
Thank you. Thank you for that. I think we're all looking forward to the kind of possibilities that can come with you coming over and we going. It can be a great learning opportunities for everyone. With this, I would really like to thank Professor
Professor
Malik.
Pratyush, if I may just intervene.
Yeah, please.
Yeah. No, I think Professor Ganapati, you may be interested in knowing, we just finished a global connected summer school where we had students from my university, Navrachna University, working on a project with students of the University of Arizona, as well as another group of students working at the Liverpool University campus, China. And they were all, groups of about six students, but each group were students drawn from all these 3-4 places of the world and working on different projects like in healthcare, in education, and so on. And so it was an entirely virtual project, kind of a summer school, driven by a professor from the University of Arizona, whom I had worked with earlier extensively. So we can do something like that with you two, for your this project or any other project that you're talking about.
Yeah, that's what all our collaboration is about. So yeah, looking forward to doing all these things. Yes.
Good, thank you.
Can we, before we end, there is one question from Jennifer.
Hi, Ganpat. It's Jennifer Randall.
Hello, Jennifer.
Hi. Thank you for sharing this. I was wondering, I work, with students that are starting out on the computer and designing, and it's a shift from one form to another. I'm wondering if you could speak a little bit to your thoughts on like the nonlinear design process and iterative design in the realm of computational design. And I had this thought, I guess, while you were speaking about ones and zeros and absence and presence, about remembering and forgetting, and how this plays a role in design with the computer as things move quickly through design sometimes, or are left to the delete button. If you could kind of speak to some of those as you see in the process of design.
That's a very good question. That's why I presented the idea in the abstract as presence and absence and transformation and logical choices, because many of the iterative processes, and like you point out, remembering and forgetting, are all founded on similar principles. Remembering and forgetting is another way of saying presence and absence. So yes, you can design algorithms or you can design computable processes that start to provide the framework for these kinds of iterative design activities where you go in loops or feedback loops, or you go into paths that are based on forgetting something or remembering something. The people who build these software tools have not devoted the time and effort, and some of them have, I should be fair, in creating these kinds of tools that allow for reflective practice. That reflective practice is often cited as missing in computable or computational processes. But that happens when the human mind follows and works with the computable processes. But you can make the computable processes themselves reflective or reflexive, depending on what word you want to use. You can make it such. It's just that the will to make such tools has been there in pockets in the computer-aided design and architecture community, but it's not become mainstream. Mainstream, you still get your AutoCAD and your Autodesk Revit and things like that. So, but those things can be incorporated in computable processes. They're not outside it. That's what I would say. Does that answer your question, Jennifer?
Yeah, I think so. Thank you. Yeah, it is about the reflective process. So
Is Jennifer
Oh,
from your
different.
school, Ganapati?
Yes, yes.
Oh, welcome, Jennifer. Welcome to our university in India.
Thank you. It's been great hearing and meeting new people. Thank you.
Thank you.
Thank you. I hope there are no other pressing questions.
Before we end, could we have a group photograph?
Yeah, absolutely. Can I request Prunali to do the honors? Prunali?
Yes, yes. Actually, I clicked a few
You did.
pictures. Yeah, but
Okay.
I'll click one more if everyone can switch on the videos.
Yes, just
Yeah, done. Thank you.
great. Thank you so much.
Thank you so much. Thank you, Professor Ganapati, for a wonderful session today. Thank you so much.
It's been a pleasure. Thank you all.
Thank you very much. It was wonderful, wonderful to listen to you. And for our regular listeners, we'll be back with more lecture series very soon. In fact, this lecture ties up with the new lecture series that we are planning, that is going to be more on housing and in technology, and that would be led by Professor Shantanu, who is also here in the Zoom room. So I think we are gearing ourselves for more technology and cutting edge technology centric lectures very soon. Thank you and have a good night.
Good night.
Thank you. Bye.
Bye.
Bye-bye.
Thank you.